Thanks for the introduction, and thanks for joining me today. As mentioned, I'm Sören. I'm with USU AI Services, and today I want to talk to you about a project I've been working on for the past year. Just a year ago, when non-tech people were asking me what I'm doing at work, I often had a hard time explaining it to them. So what's this generative AI? What's a language model? But today it's much easier. I just tell them, you know, ChatGPT, right? We're doing almost the same at a smaller scale and with domain-specific data, but the fundamental concepts are exactly the same. And people immediately get the basic idea now because they can relate it to something they already know. And I think what this shows is that these AI technologies are now mainstream. Many people use them for their daily work or maybe to generate their homework. And we as developers can also use AI to generate or explain code, right? We have all these coding assistants, which sometimes fail in hilarious ways. But they're still often useful to get started, to get an idea to iterate on. So AI changes how we write software. We've seen that in the keynote already. But just as important to realize is that AI is itself software. Even more specific, an AI or machine learning model is a function. It's turning some input into an output. It's just created differently. So instead of writing rules, implementing the function with code, we create a system to learn these rules from examples, from data and answers. So we learn our function, or in machine learning jargon, we say we train a model. And then we can apply this model to new data, to new inputs, just like any other function. And what makes this so powerful is that we can also learn functions that we're not even able to express in rules, right? Where we don't even know how. So AI is software, but it also needs more software to work. And here's an image that illustrates this quite well. It's from a famous paper on this topic by Scala and colleagues. And at the center, it's hard to see, but this small box here in the middle, this is the actual machine learning code. And we can see it's really the smallest part, right? And it's surrounded by lots of supporting software, especially for data management, because we need to manage this data, the examples somehow, right? And it turns out that especially the software for this data management is actually often written in Scala. What's more, we still have our existing applications, our business logic, user interfaces, storage, and so on. Of course, we still need that. The difference is that these applications now use the results of our AI models to provide better value. And as you all know, these applications more often than not run on the JVM, right? When we look at the machine learning code itself, though, when we zoom into this black box here, we can see that there's a gap. And that's because most modern deep learning frameworks are Python first. Frameworks like TensorFlow and PyTorch. And that's okay. Python is very popular among researchers and has this huge data science ecosystem. But it's still good to have a choice. We might want to benefit from Scala's language features, not only for these surrounding parts, but also for creating machine learning models, for writing this machine learning code. And when our production code already runs on the JVM, we might want to stay in our environment and avoid costly context switches. So it would be great if we had a tool to build modern AI systems in Scala as well. And that's where Storch comes into play. So Storch is a Scala library for doing deep learning, for building and training AI models in Scala. It's a library I created to fill this gap we've just seen. And it's based on PyTorch. PyTorch is very popular and powerful deep learning library, but it only provides Python and C++ APIs. So what Storch does is it adds an idiomatic Scala API on top of PyTorch. And by the way, Storch has another meaning too. It's the German word for stork, the bird. And you probably know that in many cultures there's this fairy tale that storks deliver babies who then need to learn everything from scratch. So I find this quite a fitting name. But I'm not going to police you on the pronunciation. You can pronounce it as you like. So on the left here, we see an example for defining a simple neural network in Storch. And on the right, we see the same using PyTorch, using the Python API. And you can see that they look quite similar. And the similarity has two benefits. First, it's easier to learn Storch if you're already familiar with PyTorch. And it also makes it easier to port existing models over. And that's important because many existing models are written using PyTorch because it is so popular among researchers. And don't worry about the details here. We'll learn about the API shortly. But let me start with a practical example first. So let's say we have a bunch of images of cats and dogs. And what we want is a function that, given an image, tells us whether this image shows a cat or a dog. So for this image, it should tell us that's a cat. And for that one, that's a dog. And of course, here's a cat again. And since this function is hard to write in code, we want a model, a neural network, to learn that function, to learn this mapping from image to animal. And one thing we need to do this are examples. More specifically, we need labeled examples, right? We have the input images, and for each of these images, we know the correct answer, the label. And that's what we feed into our model for training. So here I have a little Scala program that uses Storch to train such an image classification model for us. And I've also prepared some example images of cats and dogs, like we've seen on the previous slide. So let's actually copy this command here and switch over to the terminal. Increase the size a little bit. And let's run this. So, and when we run this, it will load these example images with their labels and feed them into a model for training. And we're using a pre-trained model here to ensure that that we don't have to train this whole thing from scratch. And what we can see is some progress bar here, and it also shows the training progress. So from time to time, it runs the model on some evaluation images, some images the model hasn't seen during training to evaluate how good the model is. And it uses this to compute the accuracy. And we can see that the accuracy increases over time. So when the training is done here, after a minute or so, we can see that it has an accuracy of 90%. Thanks.
That was faster than expected.
And on these images, right? And what we can also do now is we can actually try it on new images, right? So let's print this nice cat we've just seen before. And now we can also run this script in prediction mode and give it this cat image. And we can see that it correctly recognizes it as a cat with a certain confidence value. All right. Let me switch back to the slides. And you can actually try this yourself with your own images. So if you go to the Storch website, to the example section, we have some documentation how to do this, how to run this. But perhaps not right away, because before trying it, you might want to learn more about how this actually works. And to train models like these, we need a few ingredients. So machine learning models operate essentially on bunches of numbers. So we need a way to manipulate those numbers efficiently. And the core data structure to do this in Storch is called a tensor. So Storch gives us really fast tensor operations, and we'll see how to work with tensors in a minute. But we also need a way, a mechanism to effectively learn our models, right? And this is done through a feature called automatic differentiation, which we'll also see later. And finally, we need some higher level abstractions to build models and to run training. And Storch has a neural network API that provides us with these abstractions. For instance, to build an architecture like ResNet that we've just used in this demo. So let's start with a low-level representation. Tensors are, again, essentially bunches of numbers, or more specifically, homogeneous, multidimensional, rectangular arrays of numbers. And a good way to illustrate this is an image. So if we have an image, like this photo of my daughter here, she had her first school day on Monday, and you can see she's very proud. It's made of pixel values on a 2D grid. And since it's a color image, we have 3 channels, one for each color, red, green, and blue. And so we can represent that image using a 3D tensor. And to work with tensors, we need a way to create them. The simplest way is to create them just from regular numbers, which gives us singleton tensors, essentially. We can also create them from sequences, which gives us vectors, and also from nested sequences, which results in a matrix. And when we print a tensor, we can see 3 important attributes. So one is the element data type, the first attribute here. The second is the shape, which for our singleton tensors is empty, and for our vector here is a single number, a single dimension of size 3. And for our matrix, we have 2 dimensions of size 2 and 3. And the third one is the device. And here it's just my laptop CPU. What we can also see here, if we look at the type, we can see that the tensor class in Storch is actually parameterized with its element type. So we always know at compile time what type a tensor has. And we can use it to improve type safety for our tensor operations. And of course, there are many other ways to create tensors. I just want to show you another example from the vision module of Storch, which allows us to create a tensor from an image. And like we've seen before, when we read a color image, we get a 3D tensor. So once we have tensors, we can run all kinds of operations on them. So to show you a few, let's create a random matrix and a small tensor from a range. And probably the most important operation for deep learning is matrix multiplication. This is used for all this learning and really super important. But what you can also do is these element-wise operations, like adding tensors or multiplying a tensor with a number. And you can see that this works like essentially like mapping over the elements, right? Mapping over the elements and then applying that operation. But internally, these operations are highly optimized. They are vectorized, so they can run in parallel and are extremely fast. So one last thing I want to show you is the GPU support. So as I said, tensors are already quite fast, tensor operations, but for training these larger models, this can be computationally extremely demanding, right? So for that, we really want to use GPUs. And if you have the right hardware, which is currently NVIDIA GPUs for Storch, you can just switch out one dependency and now you can run all these operations we've just seen on the GPU, which gives you a huge speed up boost. And of course, the Tensor API has many more of these operations, and way too many to actually show them all here. And we are continuously adding more to eventually support everything that's available in core PyTorch. So for an overview, I refer you to the API docs on the website. Okay, now we know how to work with tensors. But of course, our goal is to build and train these AI models, right? And tensors and the Tensor API are the foundation for this, but we need a little bit more. So let's see how the actual process of creating and training models looks like in Storch. To help us understand how it works, let's try to learn the simplest non-constant function, which is the identity function, using the simplest model possible. And of course, we could simply implement the identity function ourselves, like here. But for more complex functions, like recognizing cats and dogs, or answering questions and so on, we can't. So we need this generic mechanism to learn it just from examples. And with a simple function, we can better illustrate this. So here I have a very simple model, and it's made of essentially two things. One is the weights or parameters, And the values of the weights define what the model computes, its logic, if you will, right? And this is what we want to learn. So here we only have a single weight that we initialize just randomly. And the other thing is the architecture. And the architecture defines how the inputs flow through the model and how they are combined with the weights to compute the output. And it does not define the logic, but together with the number of weights has an impact on what we can actually learn and how efficient the learning is. And here we just multiply the input with our weights or a single weight, so we can just learn a simple linear function here. So let's look at our random value. And we can see it's pretty small. So can anyone already tell me what this value should be for the perfect identity function in this case? One, of course, right? Here it's pretty clear. And this is good for illustration, but again, for real models, we can't interpret these weight values. So let's create an example input to see how our model is doing. And we're choosing 39 here just randomly. And our expected output for this example, our label, is in this case just the input because we're trying to learn the identity function. In reality, we usually only know the label for just a few examples. So we apply the model to our example, and we can also already see it's pretty bad, right? We expected 39, but got 5.8. So let's compute how far off our model's prediction actually is from that expected output. And here we get a value of 33, and that's our loss or our error, right? And what we're looking for now is a way to decrease that loss because a smaller loss means a better model, right? And we could do a random guess, but that would be quite inefficient, especially if we have more weights, like I think millions or billions for larger models. So what we can do instead is rely on the fact that our model and our loss function are differentiable. And you might remember from school math that a differentiable function means we can compute the derivative or the slope. And if we can do this for the loss, we can find out how we have to change the weights to make that loss go down. And fortunately, we don't have to do this ourselves like in school, because PyTorch has an engine, automatic differentiation engine, that we can use to compute that derivative automatically for us. So we just have to change our model a little bit and add this parameter. Requires gradient to enable this gradient tracking for our weights. And then we apply our model again to the example input, and we still get the same bad result as before. But now we can call the backward method on our loss and compute this gradient. And we can actually see that the gradient is negative, which means we need to increase our weight in order to make the loss go down, right? And that's exactly what we're doing. So we update our weights a little step in the opposite direction of the gradient. And then we can see that our weight value has increased, which is good in this case. And to learn, we need to repeat these steps in a loop. And in machine learning jargon, we call this a training loop. So let's actually run this and see how it learns. So we pick, again, random values here. We start with 44. And then we apply the model to it. And we still get a pretty bad loss. So we compute the gradient, which is still negative, and we update our weight again. And then we repeat that step. And we can see that the gradient stays negative, and our weight increases with each step a little bit, right? Getting closer to 1. And interestingly, at step 15, we're actually overshooting. So now we have a weight above 1. So let's see what happens in the next step. And now we can see that the gradient suddenly turns positive. So the training kind of corrects itself, right? And now decreases the weight again. And if we continue in this, we can see that our model is kind of oscillates around or converges towards 1. So we have a good approximation of our identity function here. And the interesting thing is that this simple procedure is essentially how all AIs are trained, right? The difference is that we scale up and build larger models to learn more complex functions, like recognizing cats and dogs and answering questions. And to do this, we can use the neural network API, which is a higher level API for building these models. So for instance, to learn the identity function, we could replace our own simple model class with a linear layer from the neural network API with just one input and one output. Yeah, that gives us essentially the same result. But now we can also easily add more inputs by increasing this in-features parameter. Because in reality, of course, we need to support more than a single input. Like for an image, we have an input for each pixel, for instance, or for each word if our input is a question. And we can see that this also increases our number of weights here. Each input has one weight it is multiplied with, and then we need to combine these results somehow, so we just sum them up to produce the final output. Like the number of inputs, we can also increase the number of outputs, and what we then get is a simple fully connected neural network where each input is connected to each output. But we can also take those outputs and feed them again as inputs in another layer. And when we do that, we also want to add what's called a nonlinear activation function. And we need this to be able to learn complex interactions like think if-else expressions. And here you can see that with the neural network API, we can just compose these layers sequentially, right? And of course, we can continue this and make the network deeper by adding more and more layers. For certain problems, it's more efficient to use more specialized layers, though. So for images, we often have these filters we want to learn called convolutions. So you might remember this picture from the keynote this morning. I think Andre had it as a Hello World example. So the Storch neural network API provides different common layers essentially as these predefined modules. And what we see here is also another way, a more flexible way to create a model. So we can subclass an n-dot module and then initialize nested stateful modules or layers as layers with modules with their own weights as variables or as values in the constructor. And then we can use them together with stateless operations in our apply method to compute the output. And if we continue this and scale up even more in the right way, and the right way is what researchers are trying to come up with all the time, right? We can get to architectures that are that we can actually use to solve real-world problems like classifying images or generating actual source code. So what we see here is the resonant architecture we use in our demo. It's about 300 lines of code, so I'm not showing the full code here. And finally, here's the training loop we used in our demo. And you might recognize it's actually quite similar to the loop we used to learn the identity function. We just need a few additional things. So what we need to do here is we need to load these images with their labels and convert them to tensors and also batch them. And this is done with a data loader. I'm not going to show this here, but it's quite simple, just a few lines of code. We also need to initialize our model. In this case, the resonant architecture with two output classes, cats and dogs. We need to create an optimizer, which is responsible for updating our weights during training, and a loss function. And then we can go through our examples, and we might want to do this multiple times, or in machine learning jargon, multiple epochs for better results, so we do it in a loop. And because we can't load all the training examples into memory, we also have this inner loop here that goes through the batches we get from the data loader. Another thing we need to do is we need to free the native memory after each training step, and that's needed because the garbage collector is just too slow, so we need to do this explicitly in our case, especially on GPUs, because otherwise you can't swap, and otherwise the training process essentially crashes. So then we apply the model to our input images, we compute the loss, we compute the gradients, and use our optimizer to update the weights. And that's, when we run this, essentially what we've seen before in the demo. This will train our cats and dogs classifier. Right, and this is how you can build and train your own AI models in Storch with Scala. And this also concludes our look at the API, because I want to use the remaining time to give you a little sneak peek under the hood of the library. Specifically, I want to show you how we interact with native PyTorch, and also how we make our tensors more type-safe. So if we go to the PyTorch GitHub and look at the languages, we can see that while there's a lot of Python, a huge part of PyTorch is actually C and C++ code. And that's essentially all the fast parts. But what's more, there's also a pure C++ distribution of PyTorch, which is called libtorch. And libtorch also has a C++ front end, essentially a high-level API for building and training PyTorch models in pure C++ without Python. But we want to use this from Scala, right? So how can we do this? And as you might know, currently still the fastest way to interact with native code from the JVM is the Java native interface. And if you've ever used JNI, you might also know that it's not too pleasant to use and quite hard and error prone. Fortunately, there's a really cool project called Java CPP that can take away a lot of this pain by essentially parsing C++ headers and generating this JNI glue code and also the native wrappers that are required. And they have built bindings specifically for PyTorch as well, which is really, really helpful. So shout out to Samuel and the Java CPP contributors, because without Java CPP, Storch wouldn't exist. So these bindings essentially give us the full power of libtorch, including GPU support. But it's still the C++ API, although now in Java syntax. So we still have to deal with pointers and stuff, and yeah, it's not too pleasant, right? So what we do in Storch is we wrap that and mostly hide it and add this idiomatic Scala API you've seen in the examples. The other thing I'd like to show you is how we implement these type-safe tensors and tensor operations. So if you look at PyTorch, you can see that some PyTorch operations only work on certain types, right? And giving it a tensor of the wrong type will result in a runtime error. And we've seen that in Storch, the tensor class is parameterized with the element type, and we can use that to restrict the type so that operations like mean accept only floating point and complex values. And if you try to call this method with an int type in Storch, you get a compile time error instead. So that's nice, but we also have operations where we need to do more than just restrict this type. For instance, if we add two tensors of different data types, the output type is promoted to a type that's large enough to hold the result without losing information. And to work with type-safe tensors and these operations, we need a way to track this information somehow at compile time. Fortunately, in Scala 3, there's a new feature called match types. And match types essentially let us do pattern matching at the type level, pattern matching on types, right? And this is exactly what we can use to implement these promotion rules at compile time. So here we have this promoted type, and depending on the combination of T and U, we can return a different output type essentially. And then the addition operator just returns a tensor of promoted of the type of its input operands, and therefore we can track this type in the type system essentially and make this operation safe. And of course, we can also do the same for other operations as well, with different promotion rules. we just need to ensure that runtime and compile time promotion rules match, right? Which is sometimes not easy because the runtime promotion rules are hidden deeply in the C++ code base. But we've come up with a way using property-based tests to ensure that they match. And also here, shout out to David, who's added those tests, and also a ton of other useful stuff. So what's happening next in Storch land? So one thing we've already started is adding more architectures, especially transformers, which are the base for these language models. And while doing so, we continuously improve our operation coverage. But we also have a few other ideas. For instance, for improving performance and memory through mixed precision training, and also improving improving safety. We could do more compile time safety, not only for element types, but also for shapes and devices. And another interesting thing is immutable tensors, because PyTorch itself is very mutable. I haven't shown it, but yeah, this might be interesting to support immutable tensors as well. So yeah, and higher level training abstraction. So the training loop is pretty low level. So I think there's something we can improve in the API as well. And we'd love to see you trying out Storch and give us feedback, and perhaps even build something with it or contribute. So please go check out the website and our repo, or just talk to me here at the conference. And that's it from my side. So thanks